Welcome to Mickey Study Circle channel. In this video, we shall see how to do the stress analysis of a truss. Basically, we are going to consider a rail bridge in this problem statement. So before we start with the problem statement, let us have a brief understanding about what a truss means. A truss is a structure which is consisting of only two force members, and therefore every truss element is in direct tension or in compression. And we're going to assume that the loads are applied only at the joints, that is, the connecting points of the two members of the trusses. Next assumption is the joints are assumed to be frictionless, that is, they are supposed to be as pin joints. And next, we can just see the boundary conditions for the different types of the supports. So we have got a pinned joint wherein we are going to assume the displacement in the x and the y direction is equal to 0. And next is a slider joint in the horizontal direction, wherein we are going to assume the displacement in the y direction is equal to 0. Similarly, considering a slider joint in the vertical plane or the direction, we assume the displacement in the x direction to be equal to 0. So these are some of the basic boundary conditions that we use generally in analysis of a truss problem. So with this understanding of what a truss is, we'll just move on to the problem statement. So here we have got a small railroad bridge which is constructed of steel members, all of which have a cross-sectional area of 3250 mm square. A train stops on the bridge and the loads applied to the truss on one side of the bridge are as shown in the figure. So we need to determine the nodal deflections, reaction forces and stress for the truss system that is given in the problem statement. We shall assume the Young's modulus for all the members in the truss to be equal to 200 GPa and the cross-sectional area of each member to be 3250 mm square, and the Poisson's ratio is zero point 0.3 for every member used in the construction of the rail bridge. So before we move on to the solution, we'll just try to analyze the problem statement that is given to us. So we can just see that the rail bridge is composed of totally 7 nodes, and we will be writing the coordinates for each of the nodes in order to replicate the physical continuum as the FEA model in the ANSYS APDL software. Moving on to the planes, so we have got it as a two-dimensional plane, that is XY plane. So the total height of this particular structure is 3 meters, that is the node 2, 4 and 6. So they'll be having their Y coordinate as 3000 mm. And the maximum length of the rail bridge is 3.5 plus 3.5 plus 3.5, that is somewhere around 7 plus 3, that is 10.5, that is 10,500 mm. And then we are going to define each node, that is 1, 2, 3, 4, 5, 6 and 7, using the respective coordinate numbers. And next, moving on to the type of loads that is acting. So we can just see that at node 1 there is a load of 280 kilonewton which is acting downwards, and at node 3 there is a load of 210 kilonewton which is acting downwards again. Similarly, at node 5 and 7 we have got the loads of 280 kilonewton and 360 kilonewton magnitude acting downwards as shown in the figure. Next is the boundary conditions, that is the types of joints that we have got. So at node 1, you can just see that it is fixed. So you can just assume that all the degrees of freedom to be constrained to be equal to 0. And then we have got a horizontal slider in the node 7. So we can just assume that the deflection in the x direction to be equal to 0. That is in the y direction to be equal to 0, because the motion is restricted in the direction y, but whereas it is free to slide along the x direction. So we'll be having some degrees of freedom at the x direction for the seventh node. So this is how we analyze the problem statement. Now we shall just see how to solve this problem statement using the ANSYS APDL software. So moving on to the problem statement analysis, we'll be defining the FEA model using the link 180 element, that which we have used in the analysis of the bars in the previous videos. And the domain here is structural because we are not studying any temperature effects on the members of the truss. It is purely the forces acting on the members. And next is the Young's modulus, which is 200 GPa, the Poisson's ratio, which is zero point 0.3, and the cross sectional area is 3250 mm square. So this is common for all the link members of the truss. Next is the magnitude and the nature of the load, which we have already discussed at the respective nodes. So now we'll see what are the parameters to be determined. So we need to determine the reaction forces at the supports, the nodal stresses at each nodes, and the total deformation of the entire physical continuum, that is the rail bridge. So now we shall go for solving the problem statement using the ANSYS APDL software. So we shall just begin the analysis of the problem statement by clicking the file menu and selecting change title and enter the title as the stress analysis of rail bridge and click OK. So right click and select replot. So you can just see that the problem statement is the title of the problem statement is appearing at the bottom left corner of the screen. So this is the first step. Next is we shall select the domain. So go for preferences, click structural, tell OK. Go for processor and select the element type. Click on add, edit, or delete. So we're going to add the element. So we're going to call the element link 180, that is 3D finite STN 180 from the ANSYS APDL library. So upon clicking OK, you can just see that the element link 180 is taken from the ANSYS APDL library. So now click close. Let us add the material properties. Go for material props and select material models and select structural, linear, elastic, isotropic. So as given in the problem statement, the Young's modulus is 200 GPa, so which is nothing but 200 E3 megapascals, and the Poisson's ratio for each member is zero point 0.3. So click OK. So we'll assume that the entire truss or the rail bridge is made up of the single material, so we are not going to define it as a heterogeneous component. So just click close. So we have defined the element and we have assigned the material properties to that particular element. So now it is time for us to go for creating the cross-sectional area. So go for sections, select link, click add and enter the ID as 1 and click OK. So you can just keep this section name as truss and then enter the data, that is the link area as given in the problem statement, that is 3250 mm square. So our important key point here is whenever you are entering the units in mm square, ensure that the model is also created in terms of mm only. So as you can see that in the problem statement, the distance between each node and the height of the entire rail bridge was given in meters, and here the area is entered in mm square. So either convert the area into meter square or convert the model coordinates in terms of mm. So ensure that the area is typed as 3250 mm square and ensure the tension key is tension and compression both. Click OK. So by now we have selected the element, assigned the material props for the element, and we have also assigned the geometrical properties, that is the cross-sectional area for the element. In the next step, we are going to create the model. So we shall create the model here by using the key points. So go for modeling, select create key points in the active CS. So the active CS is nothing but the active coordinate system. So the first key point is always the origin. So enter 1 and click apply. So we'll define the second key point at the location of 1750 and at a height of 3000. So that is the second key point location. So if you're not entering anything in the Z coordinate, it is assumed to be 0. Click apply. So next is the node number 3 or the key point number 3. So in the key point number 3, the parameters are 3500 and the height is 0 because it is at the base. So click apply. Next is the key point number 4. So the parameter for this key point is 5250 is the x dimension and the y dimension is the maximum height, which is equal to 3000. Click apply again. So next is the key point number 5. So assign the dimension of 7000 and the height to be equal to 0. click apply. Next is the key point number 6. So after having entered 7,000, let us enter the next dimension, which is 8,750 at a height of 3,000 mm from the base. So click apply. Next is the key point number 7. So we have got the last key point at the base, which is at a distance of 10,500 from the origin, and its y coordinate is 0. So click OK. So now we can just see that we have defined the key points and not the nodes. So we are going to create the elements first, and then we are going to mesh it. So let us see what is the procedure. So first is we have created the key points in the active coordinate system by defining the coordinates for each of the key points that is given in the continuum, that is the actual problem statement. So now we are going for creating the lines. So go for lines, select lines again, and then select pick key points. So select lines and select inactive coordinate system. So pick node 1 to 2, then again 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. Similarly, establish the connection between 1 to 3, 3 to 5, and then 5 to 7. And also between 2 to 4 and then 4 to 6 as given in the problem statement. So now we have created the actual model of the rail bridge in the active coordinate system. We'll go for the next procedure, that is the meshing. So this is how the rail bridge looks when it is created using the key points and the lines. So next we are going to define the meshing for this. So we'll go for the next step, that is meshing, and select the meshing size. So go for size controls and select manual size, and select lines and tell all lines, and enter the element edge length as uh, leave it blank, and enter the number of element divisions as 1, and click OK. So you can just see that the discretization is being done, that is the process of dividing the continuum into elements. And next is go for meshing, select mesh and select lines and select pick all. So this is the discretized model of the rail bridge. So just go for plot controls and select numbering, and select the key point numbers to be on, and click apply, click OK. Also select the node number, so go for numbering. Apart from key point numbers, select the node numbers and also the line numbers. Click OK. So you can just see the node numbers. So now we'll apply the load as given in the problem statement. So first we are going to apply the boundary conditions, that is the constraints for the supports. So we'll just go for the load option. So select loads, select define loads, apply structural displacement, and select on key points. So pick the first key point and constrain all the degrees of freedom as 0. Click OK. So next we have got one more degree of freedom to be constrained at node 7. So it has got a slider support. So select again on key points and select node 7, click OK. But this time, since it is a roller support, the truss member is free to roll on the x direction, but its movement along the y direction is arrested. So select the degrees of freedom to be constrained as uy and uz, and enter the displacement value to be equal to 0. So click OK. So you get this. So you can just see that a simple triangle is appearing here, but there are two triangles. So which tells that all the degrees of freedom are constrained at node 1, but at node 7 it is only the degrees of freedom in the y and the z direction which is constrained, but it is free to move along the x direction. So now let us apply the loads or the forces at the respective key points. So here we are not going to use the node uh, template or the uh, uh, file for the application of the nodes, but instead we're going to apply the nodes on the key points. So the template here is fk, which indicates that the force of the key point, so comma, so this is the uh, signature for assigning the loads on the key points. So fk followed by the key point indices, that is 1, and then the direction of the load, which is fy, and the magnitude is minus 28,000 or 2,80,000 because it is 2,800 kilonewtons. So this is the magnitude of the load. So press enter and you can see the application of the load here. Similarly, fk, and the node or the key point number here is 3, that is the key point number, and next is the lab, that is the direction fy, and the magnitude of the load, which is minus of 2,10,000. So you can just see the application of the node at key point 3. Similarly, fk followed by the key point number, which is 5, and the direction, which is fy, and next is the value of the or the magnitude of the load, which is minus 280, 1 2 3 3 zeros, that is 2,80,000. Enter. So the load is applied, and similarly the final key point, so fk comma, the key point number is 7, the direction is fy, and the magnitude of the load, which is minus of 3,60,000. So this is how you can see the truss with the load and the support condition. So now we'll go for the analysis. So go for solve. So select solution and select solve and select the current load step. Click OK. So the solution is done. So now time for us to extract the results. So let us go for the general post processor and select uh, list results and select the reaction solutions, all items, click OK. So since the support is at node 1 and 7, there are reaction forces only at those nodes. So you can just record the resolved components of the forces of the support at fx and fy. So that is why I've selected all values. So at node 1 and 7 you can record the values of the forces. So these are the resolved components of the forces. So click close after recording. Now let us record the deformation. So go for list results and select the nodal solution. Select the degree of freedom solution, displacement vector sum, and click OK. And you get the nodal displacements at every node, that is the 7 nodes that we have defined at x and y, and also the sum of the displacement. So the maximum nodal displacement is at node 7, and this is the nodal displacement at 4. So this is how you can just record the nodal displacement values. Click close after having recorded. Go for plot results and select deformed shape. Select deform plus and deform, click OK. So you get the maximum deformation, that is the displacement of the truss member, and the blue shape indicates the failed structure of the truss or the rail bridge due to the application of these loads, and the white structure indicates the original structure or the physical continuum. So this is the maximum displacement. So now time for us to extract the other component, that is the stress. So enter SET in the command prompt and click enter. Now let us go for element table. Select define table, click on add, and select by sequence number ls, that is linear stress. Enter 1 because 1 is the number used to call the value of the stress for the element link 180 chosen in the ANSYS APDL. So click OK. So you can just see that it is appearing here. Click close. Now go for plot results. Select contour plot. Select element table. So by default, the LS1 is appearing here. Select S average. Click OK. And you get the minimum and the maximum stress within the member. So you can just record the values of the stresses, reaction forces, and the deformations. So if you want to just go and analyze the animation of the failure, just go for plot controls and select animate and select deform shape. Click deform plus and deform and click OK. So you can just see how the application of the load at node 1, 3, 5, and 7 is deforming the member. So this is the animation for the deformation. So click close. Now let us go for the multi-plot controls, or before that we'll go for multi-window layout. Divide the screen into two halves, that is top and bottom. Click OK. So you can just see the line numbers, key points, and the node numbers, everything is on here. So now again go for plot controls. Select multi-plot controls. In window 1, entity plots, click OK. Go for deform shape and click OK. Select deform plus and deform and click OK. Right click until replot. So you get this. So we'll just check out if the style could be on. So go for style in plot controls. Select size and shape and click on this. So this is the uh, member in its isometric view with the 3D view for the component. So let me just keep the front view of this component. So this is the failed structure showing the deformation. Go for plot controls and select multi-plot controls. So in window 2, entity plots, click OK. Go for element solution, click OK, and select strain or stress and select one mises, deform plus and deform and click OK. Right click until replot. So you get the maximum and the minimum stress that is distributed inside the member. So the original structure shows the undeformed member, and this part shows the deformed member and the stress distributed in it. So the legend indicates the colors wherein the stress of 8.3 is seen. So this is where 8.3 is seen, and the red color indicates the maximum stress. So this is the blue one, this is the red one. So these are the regions where the maximum and the minimum stresses are recorded. Similarly, the magnitude of these stresses shown here is matched with the respective color. So now let us see how to record this in the white background. So after having done this, go for plot controls and select write meta file, invert white or black, and let us call this as truss 1 for our reference and click save. So it will be saved as a meta file. So go for the respective folder. So you can just see that it is going to open in a white background like this with the values of deformation in the first window and the stress of minimum and maximum magnitudes in the second window. So go for file and save this as a JPEG or a PNG format picture. So let me just save this as a JPEG file. Click save. So you can just see that it is being saved as a JPEG picture here. So this could be used for the recording of the results. So with this, we have completed the stress analysis of a rail bridge uh, composed of the truss members and which is modeled using the Link 180 element in the ANSYS APDL software, and having recorded the deformation and the stress values for the same. Thank you all for watching.